and learn how to do product rule, quotient rule, chain rule. So we have a good idea how to do most derivatives now. But what happens when I need more than one rule? So that's what we're going to work on today. So I'm going to start by making this a little bit easier for me to give me a little bit more space to work, because that's what I'm going to need. So find the derivative. What do we see in problem number one? Well, in problem number one, I see a fraction that's being squared. So if that's the case, then what we're going to do is we're going to call this thing on the inside, this 3x minus 1 over x squared plus 3. That's our inside function, and the black function is our outside function. So we're going to take the derivative then. When we go to take dy dx, we're going to need to take the derivative of the outside function. Well, what's the derivative of the outside function? Well, it's being squared, so the derivative of something squared would be something raised to the first power. And I'm going to multiply that by the derivative of the inside function. Well, the derivative of the inside function, I'm going to need a little quotient rule. So bottom, or low, d high, less high, d low, square the bottom, and away we go. So there's my derivative, at least what I call the derivative skeleton. Now with chain rule, what was inside the black function before? 3x minus 1 over x squared plus 3 was, so let's put it back inside. So the derivative part is done. Now we're up to the simplifying part. So on the simplifying part, let's see here. So we got to do a little quick algebra. So up here in the numerator, we're going to distribute to 3. So 3x squared plus 9 minus 6x squared. Distribute the negative and the 2x would be a plus 2x. Clean that up. How about negative 3x squared plus 2x plus 9? And that's over the top of an x squared plus 3 quantity squared. But there's also an x squared plus 3 over there. So if we wanted to, let's make one big term out of this derivative. So here's an x squared plus 3 being cubed. And then we've also got a 2, and we've got a 3x minus 1. Should we distribute and multiply out all those terms in the top? No, we sure shouldn't, because if I do, I'm going to end up with a polynomial. And right now, if I said, when does this thing have a horizontal tangent, I could just set that numerator equal to 0, and I'd find out there's definitely one at x equals positive 1/3, and wherever that quadratic would happen to be equal to 0. And the bottom, of course, you don't multiply out, because if I said, where do we have vertical tangents, or where's the derivative undefined, it's at the bottom equal to 0, and it'd make things a little simpler. Don't multiply it out. So there's a quotient rule nested inside of a chain rule. What about some trig? Well, we get to some trig, things start getting a little bit more exciting. And the thing that most people can look at right here is they can definitely see that there's a 2x plus 1 inside of cosine, but what gets confusing to people is what happens with that square. What's really being squared? So my advice is always write it so whatever's being squared looks like it's being squared. Well, what's being squared? When trig people put the square there on a trig function, that means you're going to take the entire trig function, and that's what's being squared. So what we really have is a problem that looks like this. And yes, I will expect you to be able to recognize specifically what's being squared when it comes time to assess you on this. So if the square is on the cosine, you're squaring the trig function and everything with it. If the square is on the 2x plus 1, then the only thing being squared is the 2x plus 1. So write it so it looks the way it's supposed to. So now what do we have? Well, I can see that there is a 2x plus 1 that's inside of a cosine, and that's then being squared. So we've got a black function, we've got a blue function, we've got a red function. When it comes time to take the derivative, well, how are we going to handle that? So when I go to take the derivative, let's see, we'll work from the outside in again. So dy over dx, we'll start with the black function. So derivative of the black function, well, there's a 5 that's going to be along for the ride. It's a constant, so let's bring it with. And then we're going to take the derivative of something squared. What's the derivative of something squared? 2 times something to the first. And then we're going to take the derivative working from the outside in. Next is blue. What's the derivative of the blue function? Well, that would be the opposite of sine of something. And then we're going to take that derivative of the last function, the innermost function, which would be the red. That derivative would be 2. Okay, so now there's your derivative skeleton. Now we're going to work our way back from the inside out. So what was inside the blue function? 2x plus 1. Put it inside the blue function's derivative. What was inside the black function? cosine of 2x plus 1. So put that back inside the black function, and there's your derivative. Now if we clean it up, I've got, how about, I'm going to write it this way. I've got a 10. Actually, let's just go ahead and make it 20, and I'll explain the difference in a second. 20 times the cosine, or sorry, negative 20 even, times the cosine of 2x plus 1 times the sine of 2x plus 1. And that's a perfectly fine derivative. But here's what I don't know if you recognize. I could write this as negative 10 times 2 cosine of a function sine of a function. Why would I write it that way? Well, when you look at what's in red, if you think back to our days of trig, that's our double angle identity for sine. And I've really got this extra negative 10 that's being multiplied by that double angle identity. So I've got really negative 10 of those sine of double the something. Well, what was the something all along? Well, that something all along was that 2x plus 1. So another way to write this exact same derivative would be negative 10 times the sine of double the 2x plus 1s. Well, why would you want to do that? Mr. Perkins, do I have to do that? Well, you don't necessarily have to. You see those two derivatives that are both in boxes. The top one is fine. There's nothing wrong with it. The bottom one is more complex, and yes, it was harder to get to. I will tell you when it's time to apply this derivative, find horizontal tangents, find things like that. I would rather work with the bottom one because it's going to cut my work in half. But if I don't know how to get to the bottom one, then I can always work with the top one and be able to use that. So is one better than the other? Depends what you need it for. I'm a fan of being able to do that bottom one, but you have to be able to recognize that double angle identity. So file that one away. And then we got this last one, and I'm going to tell you that this last one is just nasty. It's a mess. So let's write it again so it looks the way it's supposed to. Well, what do we have? We have 2. What's being squared? Well, what's being squared is the secant of sine of x squared plus 1 is what's being squared. So again, we're going to work from the outside in. So actually, let's reverse it. So start on the inside. X squared plus 1 is my innermost function. That's inside of sine. That's inside of secant. That's inside of 2 times something squared, or that's inside of something squared and it's being multiplied by 2. So we go to take the derivative. This derivative is just awful. Let's see. This is really just, I'm going to tell you, I hope we never have to apply anything this complex, and I can tell you for our purposes we're not going to have to, but if you can understand how to do this derivative, then you truly understand how to handle multiple rules, and particularly nested chain rule. So here's my derivative. If we can get through it, we're going to call ourselves pretty happy. I see a 2. I'm going to bring it along for the ride. I'm going to multiply that by the derivative of the black function. What's the derivative of the black function? 2 times something to the first. Next color in is pink. Derivative of the pink function, derivative of secant is secant of something times tangent of something. There's our pink function's derivative. Now blue, derivative of sine is cosine of something. Now finally, last but not least, the red. The derivative of the red is 2x. And we've made it all the way from the outside in. There's our skeleton. We have everything we're supposed to have. Now reverse field. So the red function was inside the blue one, so let's put an x squared plus 1 inside the blue one. The blue function was inside of the pink one, so this is what throws people off. Inside the pink function, I have to put cosine in twice, and again, still inside that is an x squared plus 1. And inside the black function, I have a pink function. Whoops. I have an error here I need to fix. I shouldn't be putting cosines inside here. I should be putting what was originally there, which is sine. My apologies. Back inside that function. And then here I've got secant now. Well, inside secant we had sine. inside sign, we had x squared plus 1. So just to kind of sum all this up, we took the derivative of the colors going from the outside in. Then when we reversed our field, we filled the red inside the blue, we filled the blue inside the pink, we filled the pink inside the black. And I'm going to tell you that yes, you could take the 2x and multiply it by 4, but I'm more worried about whether or not you can find this derivative, because the simplification I hope we never have to do. But if you can do that, you can do just about any chain rule problem, no matter how nasty.